Hi, so I'm back again for the second video in this series that is going through the Griffiths textbook on introductory quantum mechanics. So the last time in section 1.1 we came up with the Schrödinger equation. So we have IH bar del psi del t equals negative h bar squared over 2 times the mass del squared psi del t squared. So this is our wave function is psi, because a function that satisfies this equation will be in the form of a wave. Now, in the next part of the textbook, this is perhaps the most philosophical that we're going to get before we really understand what it is that quantum mechanics does. So I guess this is kind of going to be the teaser for you to stick through with these videos until we get much further in the end, where I can justify the assertions that I'm going to tell you now. So what we have with a wave function is we have a statistical interpretation of it. And this is perhaps one of the things that gets people the most about quantum mechanics and led to the famous Einstein quote of he doesn't believe that God plays dice with the universe, which is that quantum mechanics is based on statistics and it's based on probabilities. So if we take the wave function that satisfies this Schrödinger equation, we can look at a probability. So we have our wave function that depends on x in space and t time, and we take the absolute value of that wave function squared. The reason that we do that is because we can have complex numbers in there, and we need to have our probability be a real number. So this is going to equal, and then if we take the area under that curve, we integrate this, we are going to have the probability of finding the particle in a region described by dx. So if we go from x to x plus dx, so it's the probability of finding the particle from x to x plus dx. Okay. So what this means is that, say we go ahead, let's just draw a picture here, like they did in Griffiths. So this is like the picture in Griffiths figure 1.2. Okay, so I'm going to draw it out here where we have our x-axis, and on the y-axis I'm going to have the wave function squared. And then we just have something there. Okay. This y-axis is the probability. And we can call this a point A, and we can call this over here point B. Now, the probability of finding it anywhere over all space, because this function is existing over all space. So the question is, what does this really mean? What's our probability that we can find it at x equals a or x equals b? So first off, if we take over all space negative infinity plus infinity, this whole area of the wave function squared. That's represented by that integral up there. So that represents, if we took the whole area, that would be a 100% probability. So all this red shaded in area is going to add up to 100%. And then just looking at the way that I drew it, the place where it's the highest here means that it is more probable to find the particle in position A than it is to B. And that's just the way, that's why we drew it this way, because this point here at A is higher, has a higher number of probability than the part B. And if we said, like this is our x and that's dx, then the probability, the integral that I drew up there before would be the probability, would be the number to find the particle in this area. So the thing about this, I guess, that, and this is like one of the first things that becomes perhaps confusing about quantum mechanics, is what does this mean that it's all based on statistics? So we don't know where the particle is in this situation until we measure it. Say I measured it to be here, I'll call that point C, just like you did in the book. So our probability of measuring the particle to be at point C is not 100%. There's not a 100% chance it's going to be in C. It's going to be some much smaller probability. So if we measure the wave function and we find it to be at point C, then we can have a question which is, okay, I measured it at time equals 37 seconds, but where was it at time equals 36 seconds? Because it has a time dependence of it. So Griffiths outlines what are really clever, and I think this is, well, maybe not so clever, but perhaps amusing, ideas of 3 positions that you could have regarding this idea. So the idea is, where was the particle right before I measured it? I measured it to be at point C. I know that point C was only a probability. So say my probability to find it at point C, so we'll have psi of x equals ct squared. We can take out, we can say it's like this, x plus dx. I'm going to just erase this part here to make it a little bit more exact. So our probability that we measured the particle between x and dx, and that yielded a result of x equals c. That was the answer that we got from this. Our probability equaled just some number. So our probability could be, let's say our probability ended up being 37%. And then c was bigger than x and less than dx. So we calculated that we had a probability of only 37%, say, to find the particle at point C. We did a measurement, we found the particle at point C. So where was it right before we did the measurement? Was it possibly at point A? Was it possibly at point B? Or was it at point C all along? So here come the three positions that Griffiths outlines, which is, he calls the first one the realist position. And if you have the book, I'm not going to read exactly what he says, I'm going to paraphrase, but yeah, it is quite amusing. So the realist position is that the particle is at point C. And this is where we get the whole God doesn't play dice with the universe famous quote, which was that this position is that the particle was at point C and it was at point C all along because we measured it to be point C. So we measured it to be at point C, so that's what it was. That was reality. Ergo, the realist position. Now, the problem with this is that we do have this probability function over here. So what does that mean? So if we solve the Schrodinger equation for a wave equation, the nature of that solution, the nature of that wave equation is something that describes everything about the particle. It's, that's why we went through the exercise of finding the wave function. So we could find a function that tells us everything about the particle. But if we try to find the position of the particle using this function that we defined as something that has everything about the particle in it, what we get is a probability. We don't get a number out of that. So that would make quantum mechanics an incomplete theory, because if the realist position were true, that would mean that this probability function basically is not true. And the justification for this, at least at the time of Einstein and others, or at least more in the early days of quantum mechanics, was that the incompleteness of the quantum theory, the indeterminacy, so the way Griffiths puts it, of that probability function is a reflection of our own ignorance and not a reflection of the way that nature really is. So in this idea, it would be that psi is incomplete. So for this position to be true, it would have to be that the wave function does not describe everything about the particle because we measured it to be at point C, and that's where it was all along. Okay, the next position that Griffiths outlines is the orthodox position. And spoiler alert, this is the one that's actually real. Because we can do experiments, and the orthodox position is the one that we can experimentally prove. So there's your spoilers, but I'm going to go ahead and outline it, and then, many videos from now we will prove that. Okay, the orthodox position is that the particle wasn't really anywhere. And you've probably heard this in terms of Schrodinger's cat. So, you have a box, you have a switch that depends on a wave function. Your wave function can either be, we'll just say it could either be up or it could be down. We don't know. It's a wave function. It has both states in it. Once we do a measurement of it, and then say if we did a probability of it, we would find like a probability that it's in state up, we would get 50%. So if we measured it in state up 100 times, we would get state up 50 times, and we get state down the other times. But that wave function, say you have a physical mechanism that depends on the state of the wave function, so if it's state up, then it hits a trigger which releases poison gas, and it kills the cat inside the box. If it's wave function down, then the cat's alive in the box. So there's a 50% probability that the cat's either dead or the cat's alive. So the Orthodox position is that there is no state. It was both states until the measurement was done. So going back over here to this graph over here, the wave function, it wasn't like the wave function or the particle was here or maybe here or maybe here, and it's moving with respect to time, and we chose a time, the time that we chose to measure it just happened to be when it was at C. The Orthodox position instead is, that would be more like the realist position. The Orthodox position instead is saying that there was no meaning to the particle having a position until it was measured. The particle wasn't really anywhere, or you could even say the particle was everywhere. The particle was in all the states until we measured it. So this is also called a Copenhagen Interpretation. And there's a quote here from Jordan, who said, quote, "Observations not only disturb what is to be measured, they produce it. We compel the particle to assume a definite position," unquote. So, and that's from an article by Merman of solid state physics fame, in an article called "Is the Moon There When Nobody Looks?" That's from 1985. But I think that sort of sums it up, that the particle didn't really have a position, or the particle had all positions until we measured it. And once we measured it, we forced it to take a position. So once we measured it, it assumed that position, and that would be what you would call a wave function collapse. So if this is what it looks like before the measurement, we take the same wave function probability, except after the measurement. So we have a C, A, and B. So our x-axis is the same. And that would actually be, we can draw it more exact than that. So this would be something where it's the probability is 0 everywhere except for C. And then if we took that area under this curve, so that area will equal 100%. That would be like a Dirac function. So this is what it, so this would be the after the measurement. So that's our wave function collapse. Our measurement forced it to be in a position. And that's, I think, as I said, this does turn out to be the position that is supported by experimental results. It also happens to be, in my opinion, probably the most misunderstood thing about quantum mechanics. The third position that he outlines was the agnostic position, and this is the one that sounds the most reasonable until we had experimental results. So the agnostic position was to refuse to answer, which is really funny. And then that's how it's explained by Griffiths. But the idea, and this is another thing, the reason I'm going over the agnostic position is because this is something that shows up when a lot of people who don't know about quantum mechanics, like, Deepak Chopra, they sort of fall back on this. They take a weird mixture of orthodox and agnostic position on it. So the agnostic position basically says that there's no way to measure where the particle was before we measured it. And then once we measured it, the wave function collapsed and it's only going to yield that result. So we're never going to know the answer. So in a nutshell, why bother thinking about it? And then there's a quote by Pauli that says, quote, "One should never rack one's brain about the problem of whether something one cannot know anything about exists all the same than about the ancient question of how many angels are able to sit on the point of a needle," unquote, which is actually, I think, very similar to, as James Randi puts it, the atheist by the second definition. So that's, which I just realized is really funny because he would say atheist over agnostic, but then I just said that that's agnostic. Yeah, whatever. I'm talking about math, not religion. Anyway, so the agnostic position is that there's no way of ever knowing, so there's no point in really thinking about it, which is not an unreasonable position to assume about many things, but it doesn't mean that something is unknowable. So before we had experiments to test the assertion of which one of these three positions was perhaps more reflective of reality than the other one, then agnostic position was perfectly reasonable. I think the problem with the agnostic position is when we attempt to extrapolate it out into saying that just because we don't know how to test this or measure this now means that it is untestable and unknowable. So there's a difference between saying this isn't a useful question for us to ask right now because we don't have the tools to test it, versus saying this is a question that is off limits, so nobody should ever think about it. So agnostic is a big old question mark, and then, kind of a whatever. But like I said, we know that the Orthodox position is right, and that comes from 1964, and John Bell showed that there's an observable difference if the particle has a precise, though unknown, position prior to the measurement. So if, say, we had the particle was over here, and then it moved over here, and then it moved over to C, if that were true, when we did the measurement to find that it was at C, we would see a difference. And that's something that's going to take a lot of work to justify. And that's kind of where it comes down to with quantum mechanics, is that without doing the work and understanding what quantum mechanics does, any assertion to any one of these opinions is kind of meaningless. So the goal here is going to be to prove the Orthodox position, and to show what a lot of the misconceptions are about that Orthodox position. And here's another spoiler alert. Has nothing to do with humans and our perceptions. An observable is a mathematical um, quantity. It's a certain type of mathematical operator. An observable has nothing to do if humans looked at it or not. Um, the wave function collapsing, it's not just that a wave function collapses whenever people look at it. Wave functions collapse all the time by themselves. So yeah, we found out that the sun doesn't go around the earth. The earth goes around the sun. It's not even the closest planet to the sun. The sun is just one of many suns. There's planets around other suns. We're not even the center of the galaxy. We all found out that we were really, really unimportant. And then I think quantum mechanics came along and had this idea of observers. And then we kind of, at least some, you know, Deepak Chopra, people are trying to reassert our human importance with bad misinterpretations of science. So, yeah, we're still not important. But that's going to be kind of it for philosophy. And next, we're going to be getting into probabilities.